Okay, so let me remind you about acceleration. So the average acceleration of some object will be how much its instantaneous velocity changes by over time. The units are meters per second or meters per second squared if you want to express it more compactly. And again, I mentioned that this kinematics variable is definitely the most abstract of them all, and so I want to spend some good quality time with this today, doing some tangible numerical examples so that you can come out of it and feel like you have an intuitive sense of what acceleration really is. There's a lot of misconceptions about what acceleration is all about, and I want to try to at least quell some of them today. So let's just jump right into an example. Let's do it with numbers. I'm going to have a person that has an instantaneous velocity initially of plus 3 meters per second. I'm going to assume plus is to the right. I guess shouldn't take that for granted. That's certainly not going to be the case throughout this course, so it's always good form to indicate what you mean by positive. So that's their initial velocity. And then over here, let's say they have a different velocity. So the final velocity will be plus 5 meters per second. And I'm going to draw that arrow longer simply to indicate that's a larger vector. It's a faster speed, right? So it's not that someone literally has like a spear sticking out of them when they're running. This is just an arrow to represent what they're doing. And the longer I draw that arrow, the more larger it is. And let's say that this takes 2 seconds. So this is 2 seconds later. Now, first of all, before I do anything else, let's just take a quick poll here. How many people think that this motion, I'll give you the choices in advance, speed up, slow down, or constant speed. Okay? So how many people would characterize this as speeding up? Okay, almost everyone. That is correct. This is a speed increase, so this is speeding up. And the acceleration can tell us something about that, so let's compute the acceleration. The average acceleration during this trip is v final, which is plus 5 meters per second, minus v initial, which is plus 3 meters per second. And the time it took to make that change, well, it happened over the course of 2 seconds. So if we simplify this, we have a change of plus 2 meters per second. It happened over 2 seconds. And we can, of course, even divide the 2's out. So that's 1 meter per second per second. So the average acceleration during this trip is we have to add 1 meter per second every second on average. Okay? So the acceleration is we have to add plus 1 meter per second to the velocity every second on average. Let me ask you this. If we have to add 1 meter per second to the velocity every second on average, 1 second into this trip, remember the whole trip is 2 seconds, but 1 second into it, does that necessarily mean we're going 4 meters per second? No. No, it doesn't. That's like me asking the class, well, the homework's due next week. Are you going to have half of it done halfway through? I know that's not true, okay? Halfway through the week, I can go into those WebAssign logs, and yes, there are logs. I can tell exactly what you did and when. I'll go halfway through the assignment period and see that most people haven't started. Okay? So it simply means, of course, if during the first half of the week you haven't done much of anything, you're going to have to cram it into the second half, right? That's the same thing here. This simply obligates us to add plus 1 meter per second to the velocity every second on average, which means if we don't add that much in the first half, the first second, we better have a big job to do in the second half. Okay? So this just simply says this is what you have to have average out. So that's why I give you a week to do the homework and I don't try to micromanage how you do it. You can do it however you want, right? You just have to average out to having 100% of the homework done in the time period that I give for you to do it, right? So I am going to suppose, though, that maybe let's do it slow and steady. This is how I encourage you to do the homework, right? I try to give you the best tips. Don't try to start it the night before, especially starting around homework 4 or 5. You're going to be hating life if you try to take that approach of starting the night before, because the homeworks can take a lot longer. If I forgot to mention it before, every homework in this class is harder than the homework before up until about homework 4 or 5. So be prepared to spend more and more and more time. And I always encourage the slow and steady approach, and I'm going to say, let's take that approach here. Okay? So I'm going to say, not only should I add 1 meter per second to the velocity every second on average, let's do it consistently. Okay? So this is a state of motion called constant acceleration. It's a special kind of motion which is important. And it's in fact the most complicated motion that we're ever going to get to. So I am not going to entertain procrastination approaches or anything like that. What I'm going to do is that when we have a change in velocity, we do it nice and steady. Okay? So in this case, what we say is that we're going to add plus 1 meter per second to the velocity every second, and not just on average, but consistently. So we're going to make our velocity change here in a nice, smooth, and controlled manner. We're not going to procrastinate it and cram it all into the end. Now, constant acceleration, what that means then, is if we think of the acceleration as the instruction set for the velocity on how to change, we're going to think of that instruction set as being consistent. In other words, we're going to say that the reason why the average comes out to be what it is because it's literally that at every moment. So I mentioned that this is going to be oftentimes how we connect these two, is the reason why the acceleration has the value it does is because it's not just that on average, right? You didn't just finish 100% of the homework in 100% of the time window. You literally chipped away at it evenly every day, right? You got an even amount of points every day. So what I can do here, just to try to help you visualize this value that we computed, this is not just what we have to do on average. I'm going to imagine that there's an instruction set, and let me write it in its compact form here, meters per second squared. I'm going to imagine that there's an instruction set whispering into the ear of the velocity and telling it what to do next. So if we look here, the initial velocity is plus 3 meters per second. The acceleration says, psst, hey, you know what you should do in the next second? You should add 1 meter per second. Okay? So then, 1 second later, what's the velocity? 4 meters per second. So let me draw that right here. So this is 1 second later, 1 second in. Here's my velocity, plus 4 meters per second. So what to do next? Well, the acceleration is still there, saying, psst, hey, you know what you should do in the next second? You should add plus 1 meter per second, right? The instructions are always there. This is what you should do next, okay? So 1 second later, it's at another meter per second. Maybe the instruction set's still there. Maybe we don't care anymore, but maybe the acceleration is still there and saying, psst, hey, you know what you should do in the next second? You should add plus 1 meter per second. So 1 second after that, what's it going to have a velocity of? 6 meters per second, then 7 meters per second. So you can see we're adding it on nice and steady. That's what constant acceleration means, is that you're making a nice, steady, smooth velocity change. You're not procrastinating and making it up later. You're going to smoothly change from one velocity to another. That's another way to think of what constant acceleration means. smooth velocity changes. Nice and steady velocity changes. It's the case that we'll look at most often. If we're going to change velocity at all, we're going to change it in a nice, smooth, consistent manner. We're going to connect two different velocities smoothly. So this is the first thing I do want to bring up. Make sure you can understand the difference between constant acceleration versus constant velocity. These are two different things, and you're going to get jammed up very, very early in the course if you can't tell the difference between those two. Constant velocity means your acceleration is what? 0. You're not accelerating at all, right? Your acceleration is 0. The instructions for how to change the velocity are turned off. So your velocity isn't changing at all. You're just going along at a nice constant velocity. Your acceleration, which is the thing that informs how the velocity changes, is saying, hey, you don't have to do anything different than you're already doing. That's not to be confused with constant acceleration. If you have constant acceleration, well then, and I guess I should say a constant value that's not 0. 0 is a constant as well. But if you have a constant acceleration that isn't 0, it means that the instructions for the velocity to change are turned on, but they're always telling it the same thing. So they're telling it, hey, this is what you need to do in the next second. Okay? So you have, think of constant acceleration as constant instructions of what to do next. So what you're going to see, again, smooth velocity changes. The velocity changes, but it changes in a nice orderly manner. Okay? You're going to connect one velocity to another in a nice, steady approach. Okay? So make sure you understand the difference between constant acceleration and constant velocity. Are there any questions on that so far? Yeah? Yes, there is. So notice here that at every point, I've assigned an individual acceleration. It's just that it's always saying the same thing, right? Now you could have, maybe your homework approach is like the acceleration is 0 at first. Hey, you don't have to get anything done. Don't change, don't change. And then midweek it's like, you better do something about this homework assignment. It's about to be due. And then your acceleration has to kick up to a much higher value, right? But what I'm saying is let's not do that, right? So even though you can assign an acceleration to every point, let's have it be the same thing, right? So to give you an example, somewhere between the 0 and 1 second, your velocity, let's make up a number. It's somewhere between 3 and 4. I don't know, 3.2 meters per second, right? So somewhere in between here, you're going to have a velocity of 3.2 meters per second, right? The acceleration at that moment is saying, psst, hey, you know what you should do in the next second? You should add +1 meter per second. So if you're going 3.2 meters per second here, what are you going to be doing 1 second later? 4.2, right? Because the instructions are always saying, hey, psst, in the next second, do this. Change your velocity by this. So you can assign the acceleration to every point, but it's always going to be saying the same thing. Hey, psst, in the next second, add 1 meter per second to your velocity. So during any part of this trip, if you look at a 1 second chunk, whether it be the first second or the second or any 1 second chunk in between, you can be guaranteed that the velocity is +1 meter per second larger than it was at the beginning of that second. Does that make sense? Okay. Are there any other questions? Okay, so that's a little bit about acceleration, and we will almost exclusively focus in on this, okay? So the acceleration will be constant, so while you can say that it has a value at any given point, the value is the same, always, therefore the average comes out to be the same. Average of a bunch of 1s is 1, okay? Other thing I do want to point out, and this is an important distinction, if this is 0 seconds, 1 second, 2 seconds, of course I've shown the velocity is steadily and growing. The distances are not equal, okay? So this might be halfway through in time, but it's not halfway through in distance, right? Can anyone tell me why this distance is actually a larger distance? So why is it that you cover more ground in the last second than in the first second? Yeah?
Going faster in the same time.
That's exactly right. So in the first second, you're going relatively slow. You start off at the lowest velocity you ever have, and you only speed up to 4. Whereas 4 is the very slowest you have during the second part of the trip, right? So when you're changing velocity, it's evenly in time, but it's not necessarily evenly in distance. If you're going faster and faster and faster, you'll cover more distance in a given time, okay? So make sure you don't mistake adding velocity evenly with time, right? After 1 second, you've gained plus 1 meter per second. And then you've added plus 1 meter per second again. Remember, it's plus 1 meter per second every second, right? It's not plus 1 meter per second every meter, right? So make sure that you don't mistake adding the velocity evenly in time with the evenly in distance, okay? So this is a shorter distance, and this is a larger distance. So that's just one example. Hopefully the speeding up part was fairly intuitive. Most of you answered that it did speed up. And so I had a chance to focus a little bit on the differences between just having a certain acceleration on average versus what we call constant acceleration, where you make a smooth and steady velocity change. Now, what I want to do next is do some other cases where you do have acceleration. They're going to be basically like this example, but just with the numbers switched around a little bit. So let me do a similar one. So let's say that instead, our initial velocity is plus 5 meters per second, and the final is 3. So I just reversed the initial and final velocities, going to still have the same time period. Okay, so is this object speeding up, slowing down, or constant velocity? How many people say speeding up? How many people say slowing down? Excellent, it is. It's slowing down, and I've already drawn the vector shorter to indicate that. So this is a slowing down. Let's do another poll here. For the acceleration, is it going to be positive, 0, or negative? How many people say positive? How many people say negative? Okay, almost everyone. That's right. In fact, if you computed the average acceleration, try it yourself. Hopefully it's not surprising that it comes out to be negative, because all I did was reverse the initial and final velocities. So if you subtract them in that order, you'll get a negative instead of a positive. Okay, so what does that mean? It means, of course, we have to add minus 1 meters per second to the velocity every second on average. Again, if that's all you knew, you're not guaranteed that you did that smoothly, right? Maybe you've been driving behind someone that suddenly slams on the brake like 2 feet before the light, and you almost hit them, right? So it doesn't have to happen steadily, but let's assume that it does. So let's just say we have constant acceleration, which means that we're adding negative 1 meter per second every second. It's smooth. So there's a little instruction set whispering to this velocity, hey, you know what? In the next second, you should add negative 1 meter per second. So that'll mean that after 1 second from the beginning, what's the velocity now? Plus 4, right? Where should I draw that, by the way? Should I draw it here in the middle, or to the left or right of that? I'm going to draw it to the right. I'm going to cover much more ground here in the first second. I'm slowing down, which means that I'm going to cover more ground at first and less ground later, right? True? If you slam on the brakes while you're driving 50 miles an hour, the first second you're going to go way far, and just before you stop, you might go a couple inches, right, in a second. Okay? So, again, the distances are not equal. Okay? So this distance is larger than this distance. Okay? So there we have, after 1 second, the instructions are constant acceleration, minus 1 meter per second squared. So it says, hey, in the next second, you should add negative 1 meter per second. And then, of course, there we are at the end. You're at plus 3 meters per second. If we kept doing it, if we kept on applying this acceleration, what velocity would we have 1 second after this? Plus 2, then plus 1 meter per second, then 0. What happens then? Well, we'll take a look in just a second. Okay, so there's a case. We might normally call this deceleration, right? But deceleration is just a fancy English word. We generally don't, we just talk about acceleration, right? So acceleration has different ways that it can point, right? So this happens to point to the left, whereas in the previous one it pointed to the right. Okay? Let's do one more, just to kind of test your intuition. Especially if you've seen in high school physics even a little bit, a lot of times you develop some bad habits. One of the bad habits you develop is that things always go to the right, and you get too used to that, and you start to get things that you can't handle it when it goes to the left. So let's try it. We really should be able to have something go on the number line to the left. So let's say that the initial velocity is, I don't know, let's say minus 5 meters per second. And then over here, it'll be, the final is minus 3 meters per second, and that'll be 2 seconds later. Now, before I draw the final arrow here and give it away, how many people think this is speeding up? How many people think this is slowing down? One person? How many people just don't know? It just going to the left kind of threw them a little off there. Well, let's try it again. So how many people think it's speeding up? Okay, how many people think it's slowing down? Okay. There's 3 people, 4 people, 5 people. That is correct. Okay? This thing is slowing down. Okay? So, what happened here? The mistake you can make is to compare these like they're on a number line. If you're comparing minus 5 and minus 3 on a number line, you might say that 3 is higher on the number line. But that is not what you should be doing. Remember that the sign indicates here just direction. So that just indicates to the left. You should be comparing the numbers. So if I were to instead ask you, which is faster, 3 meters per second to the left or 5 meters per second to the left, you'd probably say that 5 meters per second to the left is faster, and then this is slower. In fact, that's why I'm going to draw the arrow here. It is a smaller speed. It's to the left, but going 3 meters per second is going slower than going 5 meters per second. So the way to compare here to see if something's faster or slower is to see if it's further or closer to 0. 0, of course, is the slowest you can be going, which is 0 speed. But 3 meters per second in the positive direction is equally fast to 3 meters per second in the negative direction, right? They're both 3 meters per second, and there's no difference between going to the right and to the left. So you can't take the minus sign literally like you would have in math class. So you are slowing down. All right, so let's do a poll on the acceleration. Okay, so how many people think the acceleration is going to be positive? Positive? Okay, how many people think the acceleration is going to be negative? Okay, how many people don't know? Okay, so you can see that just having stuff going to the left really threw a wrench in the works. You guys got everything right pretty much when we was going in the positive direction. Now, all we did was go in the negative direction, and everything is kind of all scrambled up. So the answer here for the acceleration, well, certainly you can compute it, right? V final minus V initial over time, and you will get it as a positive. The acceleration comes out to be plus 1 meter per second per second. Of course, that's technically just the average, but we're assuming that that is also the value at all times, just to make our lives easier. Now you might say, wait a minute. How did that happen? Over here, we were slowing down and the acceleration came out negative. Over here, we were slowing down and the acceleration came out positive. Okay? Well, think about it like this. This said to add negative 1 meter per second to the velocity every second. Well, if you're adding a negative number to a positive value, you're going to make it smaller, right? You're going to make it closer to 0. You're going to slow it down. But over here, if you're adding a positive number to a negative velocity, well, of course, adding a positive to a negative is going to make it closer to 0. Okay? So here, you have to add plus 1 meter per second to the velocity every second. In my first case, of course, you're adding positives onto a positive, so you're making it go faster. But here you're adding positives onto a negative. So you're going to make it shrink. This is what happens when people get too accustomed to always going to the right. They think that positive acceleration means speeding up and negative acceleration means slowing down. That is incorrect. Okay? You can see here, this is a positive velocity that is slowing it down. So what's the common thread? This is the rule of thumb that you can use. When the velocity and acceleration point in the same direction, then you speed up. So think of it as the acceleration instructions are reinforcing what the velocity already has going on. So if the velocity, for instance, is positive, then a positive acceleration will make it speed up. That was my first case, case 1. I guess I forgot to label them, but case 1 is the one I erased, and then this is cases 2 and 3 here. Okay, so my case 1 was when the velocity was positive and then the acceleration being positive built on made it bigger. It could also be that the velocity is negative and the acceleration is negative. Then what the velocity's got going on is already negative, and putting a negative on top of that makes it bigger, makes it further from 0. If they point in opposite directions, then you slow down. If the acceleration is opposing what the velocity already has going on. So if the velocity is positive, but the acceleration is negative, that was my case 2, then you'll slow down. Right? It's right here. The velocity was positive, acceleration is negative, so you slowed down. It's because the acceleration was taking away from what the velocity had going on. But if the velocity itself is negative, then a positive acceleration will take away what it has going on. That was my case 3. So I want you to get that out of your head if you have it jammed in there. Okay, positive acceleration does not necessarily mean speeding up. Negative acceleration doesn't mean slowing down. It depends. I want to point out that it's possible for negative acceleration to speed something up and positive acceleration to slow something down. Okay? It's all about how do the two relate. If someone just hands you the acceleration and says it's plus or minus and asks you what the object does, you say, I have no idea. Give me the velocity. I need to see how the two relate to each other. I need to see if the velocity and acceleration are reinforcing each other, in which case you're going to speed up, or I need to see that the acceleration and velocity are opposed, and that's why it's going to slow down. Okay, so that's kind of a major conceptual idea. Are there any questions on that? Yeah. Yes, exactly right. So the plus and minus, for us so far, the only thing that plus and minus indicates is direction, right or left. Mm-hmm. So you can see I drew it as a negative here. It's negative, so it's to the left. And likewise over here, the acceleration was positive, so I guess I should have probably shown it here as going in the positive direction. And that's opposite, of course, the velocity. So it's against the velocity. Are there any other questions? Okay. So I think we have one more order of business before we just kind of jump in to some interrelationships. This is our final kinematics variable. The only thing that I want to address, I've already touched upon it briefly over here. There's only so much you can slow down before there's no more slowing down to do, right? There's only so much you can slow down before you stop. So we should probably examine that, right? There's a little bit of an asymmetry. If you speed up, you can speed up forever. You can't exceed the speed of light or whatever, but if you neglect that, okay, there's no problems with speeding up more and more and more. But you can only slow down so much before there's no more slowing down you can do, right? You stop. So let's make sure we understand what happens there. So just so I don't have to wait forever to slow down to a stop, let me start with a velocity that's a lot smaller. So let's do a little chart here. A time versus velocity. And let me suppose, for instance, that the t equals 0, and I'll put the column headers, the unit there, so I don't have to write it on everything. So that'll be in seconds. Time is in seconds. Velocity will be meters per second. And let's start somewhere not too fast. And let's suppose we have a constant acceleration of -1 meter per second per second. Okay, so after 1 second passes, what's my velocity? +1, right? That's the rule. I have to add +1 meter per second to the velocity every second, right? So I have to add -1 meter per second. Okay? How about after 2 seconds? What's my velocity now? 0. I've slowed down so that I've stopped. So there's my acceleration. I again removed 1 meter per second. And that's second. Let me sketch what this looks like. So let me sketch it on a number line with the positive direction to the right. What does this look like? It looks like this. +2 meters per second, +1 meter per second, and stop. That's my velocity. And I guess I can draw my acceleration in red again. So, and I guess I should label that here you're stopped. 0 meters per second. Now this is where a lot of people's intuition about, like, say, from vehicles and stuff like that, may not quite line up with what you think might happen. Now in a car, when you slam on the brakes, right, what are you doing? You have a forward velocity, you slam on the brakes, the acceleration's behind you, right? So they're opposite, and you slow down. But when you hit 0 velocity, what does the acceleration of your car turn into? Well, let me ask you this. Once your car is stopped, it stays stopped, right? So the velocity is 0, 0, 0, 0, 0. So is the velocity changing? It's not changing anymore, right? So the moment you hit 0 velocity, your car also says, okay, I'm done, 0 acceleration. So that's often the case with things like brakes is that the velocity and acceleration are opposite only when the velocity isn't 0. But when your velocity goes to 0, your acceleration shuts off too. So then you just stay at a constant velocity of nothing. So that's an acceleration that is only acting when you're in motion. It's actually a more complicated profile. So what I'm about to suggest is a more simple profile where just because you stop, the acceleration doesn't stop too. And so I'm going to suppose that even though I have stopped and I'm at rest here, that the acceleration, that instruction set on what to do next, is still there. And we have to follow it to the letter of the law. Okay? So let's say we let 3 seconds pass. If we keep on following the rule, what is my velocity now? -1. Right? I have to keep following the rule. I have to keep adding -1 meter per second every second. But after 4 seconds, what is it now? -2. Keep having to follow the rule. So what's going on here? Well, there's really 2 parts. This part, the first 2 seconds, my velocity is positive, but my acceleration is negative. So we learned if that's the case, what happens when they're opposed? You slow down. But now, there's only so much you can slow down before you stop. From 2 seconds onward, what's the sign of the velocity? Negative, which means what? You're going to the left, right? You turned around. And the acceleration is still negative because it's constant. So what happens when the velocity and acceleration are the same direction? You speed up. So if you apply an acceleration opposite your velocity long enough and you just let it maintain and persist, what it will do is it'll slow down, stop, turn around, and speed up an object. So I can draw this. I guess I can, just so it doesn't get cluttered, I'll do it down here. It looks like this. So you stop, turn around, and speed up in the other direction. The acceleration is now helping the velocity. You can kind of think of it as the acceleration says, come on, you want to be negative, you want to be negative, you want to be negative. Okay, now you've got you on the dark side, right? So now the velocity could only resist for so long, being positive, then it turned 0, then it turned -2. Because the acceleration just keeps on adding that -1 meter per second every second until the value is negative. And so it speeds up going in the other direction. So notice that persistent acceleration says, come on, negative. Negative is where it's at. And the velocity goes from positive to 0 to negative. Okay? Now, how could you experience this in a car? Well, you can't use your brakes, because the problem with the brakes is that when the velocity goes to 0, the brakes don't do anything anymore. Okay? One thing you can do, and I don't recommend doing this because you'll probably wreck your car, is when you're driving forward, instead of taking the brakes and turning on the brakes, put your car in reverse and hit the gas pedal. Okay? So don't try this too fast. Okay? Maybe just very slow crawl in the parking lot, but you can actually experience this. What happens when you throw your car in reverse and you hit the gas? It points the acceleration behind you. And it points it behind you permanently, right? So your velocity is forward, but your acceleration is backward. So what's the first thing that happens? You slow down, you stop, but then, of course, you're going to do what you normally do from rest, which is that you speed up going backwards, right? You're supposed to only apply your acceleration vector pointing behind you when you're starting from rest, and then you just speed up going backwards. But you can do it, and this is where you get into car problems, when your velocity vector is forward. You apply your acceleration backwards. You slow down, you stop, and then you turn around. Sometimes when I'm like trying to maneuver out of a parking space or something like that, I get lazy and I don't want my car to stop. I just kind of put it in reverse a little early. Have you ever tried this? So you feel it slowing down and speeding up. Now, you don't need to wreck your car to see this. I'll give you another example. Okay? An object that slows down, stops, speeds up in the other direction. Here we go. Something just like that. It slows down, stops, speeds up in the other direction. It's because gravity applies a downward acceleration. Okay? Just take a look at this picture like this. Okay? So what happens is gravity applies a downward acceleration. In fact, we're going to learn next lecture that it's constant. It's largely constant. So what happens is that if you have a downward acceleration, but you toss something with an upward velocity, right? I throw it up in the air. What happens first is that the acceleration, being opposite the velocity, chews off that velocity. It chews it to 0, and for a brief split second at the top of the flight, it stopped. But then, of course, it's not like the brakes in your car, right? It doesn't stop up there. Because while your brakes might stop accelerating your car, when you stop, gravity doesn't turn off. Okay? So even though your velocity is 0, the acceleration is still there saying, got to keep changing. And so what happens is the downward acceleration of gravity pulls the thing and speeds it up going downward. So it slows down, stops, speeds up. It's all happening under a single constant downward acceleration. Okay, so gravity applies an acceleration opposite the motion for long enough to stop it and even turn it around. So in one-dimensional motion, this is really the possibilities you have. So one-dimensional motion, here are the possibilities you have. This is going to be a complete list of what is possible. You can either stay stopped, which is the most boring thing in the world. So you don't do anything. Your velocity is 0 and your acceleration is not about to change it. You could have a state of constant velocity, which means that your velocity is not 0, but your acceleration doesn't want to change it. So whatever velocity you have, you just keep trucking along, and the acceleration doesn't have anything to say about it, doing something else. So those are the most boring ones, but we added several more today. So we could have that you are speeding up. If you want to go faster, it's because the velocity and acceleration are in the same direction. So now neither of them are 0, and one helps the other. The acceleration reinforces the velocity. You could have that you slow down when the velocity and acceleration are in opposite directions. Well, we've also learned that there can be life after slowing down and stopping. So we just made the point that you could, and I guess I'll put an asterisk here, you could slow down and even stop, turn around, and speed up. Because if the velocity and acceleration are in opposite directions, that might actually, if you let that go on long enough, it might not be true anymore. Because if you slow down the velocity enough to stop it, you can coax the velocity into your same direction. And then, of course, you can go back up here. That's a complete list of what can happen in one-dimensional motion. Remember, moving along a line, that's the only possibilities. We have left and right, so that's nothing else is doable. Are there any questions on that before I move forward? Okay, so now we've got everything out on the table. We've described all the variables. Now all we're going to do is we're going to develop some toolkits for how they interrelate. So let's do that. So let me just make a list of all the things that I have. Here are all the quantities I discussed so far. Those are all my quantities in, measured in meters. Here are all my quantities measured in meters per second. Here's my accelerations. And while there is a technical difference between average acceleration and instantaneous acceleration, we will generally have them be equal, right? For constant acceleration, they're equal. And then we'll have delta t or t. Now, we don't need all of these. We're just going to pick the best ones. And the best ones, well, here we don't have a choice. We're going to have to use time. Here we really only have one, acceleration. But we do have some choices. We have a number of quantities which are measured in meters per second. And I'm going to suppose, and hopefully this isn't surprising, I'm going to pick velocity. So velocity is better than speed because it has a direction, right? So it has extra information. And also you can talk about what it is at any given moment rather than a single average value for some whole trip. So I'm going to use v initial and v final. What's my initial velocity at the beginning of a trip and my final velocity at the end? And then I'm going to pick a winner from the first three, which is going to be the quantities measured in meters. Now this one, it might surprise you. I'm going to pick displacement. Common thought is, why don't I pick distance, right? Distance carries information about every step. Well, it doesn't have a vector quantity to it. It doesn't tell you direction. And it turns out that if you have constant acceleration, there just isn't that many things that can happen, right? And so we don't really need to know every single step because there's not going to be any wild surprises. Displacement will do us just fine, okay? So these are going to be my 1, 2, 3, 4, 5 kinematics variables, and those are going to be my focus because the other things, while I can always get them, they're going to kind of be off on the side, okay? They're not going to be my main line of thinking. Before I do anything else, I want to make a change of variables. So this is the same old quantities. I just want to change how they look. I'm going to remove the vector hats and instead add a subscript. While you might think that's a stupid idea, we need to remember that they're vectors. You can think of the subscript as reminding you. It doesn't make any sense for it to be x something if it's not along an x-axis. There's a very good reason for that, and I don't want for doing this, and I don't want to tell you quite yet what it is. But remember that these guys can still be plus or minus, just like they always were. Only time, of course, is positive always. And what we're going to do next time is take this list of 5 variables and flip their interrelationships every which way until we have not 1 or 2, but 5 different equations in our toolkit where we can use them to throw them at problems. So I'll introduce that toolkit next time, and then I'll do some examples with it. Okay, that's it for today.